take some questions if we have any from the homework. If you don't, that's okay too. It's not a big deal. Just kind of offering. Sophia?
Can you do number 6?
6, sure. So 6 is just asking how many triangles are possible. So we see that this is like let's see, A, B, C. I'm going to draw something out just so we have something to look at. So there's my 87, there's my 13, and there's my B. So this is an SSA situation, right? Because I have 2 consecutive sides and the angle's not in between the 2 sides. And the angle is acute. And that side B is less than side A, so this is the ambiguous case. So to figure that out, we're going to do sine of B over B equals sine of A over 13. And if I cross multiply and divide, I get that sine A is equal to 13 sine 87 over 4. And then I need to evaluate what that is, so I'll type that into my calculator. And that gives me about 3.25. And since that number is greater than 1, I know that there are 0 triangles possible. Does that feel okay? So again, I tried, I wrote a lot of stuff down, but I wanted to make sure that, it was easy to follow my reasoning on what I was doing and why I was doing things. I saw another hand over on this side of the room. Is that Allie?
Yeah, 5.
5? Okay, so the same instructions here for 5. So we have A is 130 degrees. Side A is 14 degrees and side C is 18 degrees. Again, I'm going to just draw a quick little picture to kind of make life easy to see that this is an SSA situation, right? Our angle A, though, is obtuse. So, and then we notice that side A is less than side C. So since this angle's obtuse, I know that this side has to be the hypotenuse, but it's shorter than the other side, which is like a contradiction. So that should tell me then that there are 0 triangles possible. Is that okay, Allie?
Yeah.
Okay. Gracie.
Number 8.
Sure. That would be fine. Yeah. I mean, you could have done like WXY and assumed, like it doesn't really matter the other label that you're giving it for the triangle, but that would be fine. You could use Z. Is that what you're asking? Okay. Ben?
Can you scroll up a little bit?
Sure. Is that enough? Okay. Sophia?
Can you do number 12?
Sure. Okay. Thanks, Ben. You're welcome. So 12, B is 38 degrees, little b is 21, and C is 25. So again, I'll just start by drawing a picture. I think sometimes it just helps to have something, oopsie-daisy, visually to look at. Now, to some extent, we have, in the directions, we're told that there's two triangles possible. I'm just going to run through the justification of that. You don't really need to do it for this problem, but it's just a nice opportunity to kind of review what that justification is again. Is that okay? Sophia, you're good? Okay. So we see this is an SSA situation. We see that angle B is acute, and we see that side B is less than side A. So this is the possible ambiguous case. So we can say sine of 38 over 21 is equal to sine of C over 25. And if we cross multiply and divide, sine C is going to equal 25 sine 38 over 21, which is about 0.733. And since this is less than 1, I know that I have two triangles. So that's my justification, how I know that there's two triangles. Let's go ahead now and find the values for those two triangles, which is what's asked in the question. That part that I did was just kind of reviewing how we can determine if something's an ambiguous case and like how to tell how many triangles we get. So I'll make two little columns for my work. So triangle 1 and triangle 2. And I'm going to just refer to these as, like with some subscripts, so it's a little bit easier to kind of keep track of everything. 1 and 25. So the pieces that are given are the same in both triangles, so I'm not going to bother with a subscript for those pieces. So that's kind of my setup. For triangle 1, I know from the work that I did previously that sine C is equal to 0.733. So angle C is just going to be the sine inverse of 0.733. So that's about 47.133. So that's C1, I guess I should put. C2 is just going to be the supplement to C1. So that's about 132.867. So far, so good, Sophia? Okay. Now, oops, I put those in the wrong spots, huh? I put those in the A spot instead of the C spot. Rather than erasing the number, I'm just going to erase the letter, because that's a lot less writing. Ha ha ha. So now that I have two of the angles, I can find the third just by doing the triangle sum theorem. So that should be 94.867. And similarly over here, got to remember to use the other angle C though. So that would be 9.133. Good with that? And now that we have angle A, we can find side A by using the law of sines again. So I'm going to use the given information with my new angle A. So when I cross multiply and divide, that. So that's about 33.987. And I'll do similar over here. Oops. So I have sine of b over b equals sine of a2. So I gotta make sure I change that angle. And when I cross multiply and divide, I get 21 sine 132 and change divided by sine 38. Oh, thank you. That should be 9 or whatever, right? 9133. Great. Absolutely. If you see me making a silly mistake, please interrupt before we get too far in. That saves everybody a whole lot of time and aggravation. So when I do that, I get 5.414. And just take a moment here and kind of check from just using what I know about the proportionality of triangles. So the longest side is across from the longest angle. The middle side is across from the middle angle, and the shortest side is across from the shortest angle. That triangle looks good. And the next one, I have the biggest angle across from the biggest side, the middle side across from the middle angle, and the smallest angle across from the smallest side, which also seems to match. So I'm pretty confident that these ones were done correctly. Again, that's an quick little easy check that you can do at the end. Doesn't tell you absolutely that it's right or wrong, but if you made a bad mistake, it'll catch those for sure. Therese?
How many decimal places do you want us to go with that?
I've been just doing everything to 3. And on a test or whatever, I'll be specific about what I want. But on the homeworks or whatever, if you're doing 3 or 2 or it's not a big deal. Does that feel okay? So I've been doing 3, just because I think it helps make it harder to goof up the rounding, or like if you did something a little bit wrong, it's easier to see like where it happened if you have more decimal places. Okay. Any final takers on this stuff before we move on? Okie dokie. Today, we're going to be finishing up with Chapter 7. I know that was quick, but it's not a hard chapter. Or that hard of a chapter, I guess. So we'll talk about 2 things today. The first thing we'll talk about is the law of cosines. So we saw previously that if we had an angle-side angle, an angle-angle side, or a side angle or side-side angle, that was a law of sines situation. Today, we're going to talk about what we use if we have a side angle side or a side situation. In those cases, we're going to be using the law of cosines. I'm going to put a little asterisk on the side-side angle because we know that that's a situation we have to be careful about. Similarly, we're going to have to be careful about the side-side-side situation, although it's not nearly as difficult of a check there, but we do need to be careful because your teacher can be a sneaky jerk and make that an impossible problem also. So just as like a summary of kind of what we need to do. So our law of cosines states as much. So if we have some triangle ABC with side lengths ABC, we can write the law of cosines kind of two different ways. Or, sorry, three different ways. So we can say that a squared is equal to b squared plus c squared minus 2bc times cosine a. The thing to remember about this is just that whatever side length you've got by itself, you're using the corresponding angle in the cosine, and then everything else is just the legs or the other sides fill in the other spots. So another version, if you put b squared out here, you're going to have cosine b, and then you just have a and c as the other two pieces, right? And then if I wanted c squared by itself, well, again, same idea. If you take a look at this law of cosine should look a little bit familiar. It's pretty similar to the Pythagorean theorem, just with like a little extra correction factor at the end, that minus, the other two sides times cosine is basically our correction factor for not being a right triangle. If you did the law of cosines on a right triangle, that last correction factor just zeroes out because the cosine of whatever will just drop it out to zero, and you have just the law of, you have just the Pythagorean theorem. So this is just kind of a more general statement of the Pythagorean theorem, basically. So let's do a couple of examples here using this. So just sketch a quick little picture. Oops, let's put the numbers in, I guess, instead of the letters, huh? So here we can see this is a side angle side situation. Everybody agree with that? Since the angle is in between the two side lengths in our picture. So if I want to solve this triangle, I'm going to use the law of cosines to solve for a. So I can say a squared is equal to 17 squared plus 14 squared minus 2 times 17 times 14 times cosine of 34. And that's easy enough. I can just type that kind of all into one line on my calculator, and I get about 90.378. And then I have to remember to square root both sides. And since we're looking for side lengths here, we don't have to worry about the plus or minus when square rooting both sides. We just know we're going to get the positive result, since you can't have a negative side length of something. So there's that. Now to find one of these other two angles, I can either use the law of cosines again, or I can use the law of sines. I would do the law of sines. I think that makes it a little bit easier. And it doesn't really matter which angle we solve for next. But usually what makes things easiest is looking for the smaller of the next angles. So let's find angle B next. I know B is going to be the smaller of the two angles because the side length B is shorter than the side length for C. So I'm going to do sine of A over A equals sine of B over B. And when I cross multiply, divide, and do the sine inverse, I get that B is about 55.433 degrees. Why did I do this? Why did I choose to find the smaller angle? Why does that make things easier? We're avoiding the ambiguous case. So you can't run into that possibility if we're doing that. And this is not an ambiguous case problem because we know that side angle side information at the beginning. But if you look at just the information to solve for that other angle, you could be in an ambiguous case situation, end up finding the wrong triangle of the two triangles. So that's why I recommend that. Does that make sense, guys? So again, yes, Jesse.
If you're given side, or triangle, is there going to be a certain side you want to start outlining?
Yes, and we're going to do that example next.
Okay.
Yep. Yeah. So let's do a side example now. Oh, we still have one more angle to find, right? Sorry about that. Now angle C is easy, so just 180 minus the other two that we know. And then we're done, right? Okay. So side situation. I'm not going to bother drawing the triangle because it's clear that this is side, right? Since you're given three side lengths, there's nothing else it could be. The ones where you have like two angles or, two sides and an angle, sometimes it's not entirely clear whether it's side angle side or side angle or angle side angle or angle side sort of situation. So sometimes it's helpful to just draw the picture here. We know that. Before we decide whether to do this problem, we have to check to see if this is even reasonable. I can't make a triangle out of any three side lengths, right? Like if I say, oh, make a triangle out of pieces that are 1 foot long, 2 foot long, and 65 feet long, well, that's not going to make a triangle, right? So the check that we need is that the sum of the two legs has to be greater than the hypotenuse. That's the check that we need in order to proceed. If we get that, then that's just no triangle is possible. So if that's not true, no triangle is possible. But in this case, we're good, right? 5 plus 8 is greater than 10, so we're good. So far, so good? Okay. And then for our law of cosines, then, what we're going to want to do is we're going to use the hypotenuse as our side that we've isolated. And the reason we want to do that is that you're going to get the biggest angle then, which removes the possibility of running into an ambiguous case later on. Because almost certainly this will be a obtuse angle. Now it doesn't have to be obtuse, but it's still going to be the biggest angle there, and it'll be across from the biggest side, so you'll be safe from that. That's what you were asking about, Jesse, I think?
Yeah.
Yep. So that's usually the easiest way to kind of avoid any weirdness going on. It's just to use the biggest side length there. Now I want to pause here for a moment and point out a common mistake I see students make. Well, not frequently, but on occasion. Is I see students combine these three numbers on occasion. Keep in mind that the 80 is attached to a variable, so it's not a like term. You can't combine it with the other ones. Now you look at me like I would never do that, but it's like, you know what? Under stressful situations, I see kids do that on occasion. So I'm just pointing it out to be careful about. So I'll subtract the 25 and the 64 from both sides, and then we'll divide by negative 80. And then we'll do the cosine inverse of both sides. And when I type that into my calculator, I get about 97.903, which is obtuse, right? So I know that automatically now, even if in an SSA situation, I don't have to worry about the ambiguous case because my angle's acute and it's across from the biggest side already. So I can proceed all willy-nilly with the law of sines and not have to worry about anything, which is nice, right? For the ambiguous case, you need an acute angle. And now, again, I'll find the smaller. I'll use the smaller of the, the smallest angle next when I'm using the law of cosines, or law of sines again. So that's why I chose side P over side Q. Again, that avoids the ambiguous case again. So when I solve for P, I get that, which comes out to be about 29,686. And then to find Q, we just do 180 minus those two. Which gives me about 52.411. Feel okay? Should be relatively easy. I mean, the trickiest parts are just kind of like remembering which side or angle you want to solve for next in order to avoid having to run into those ambiguous cases. But again, you do a couple of tries through and it's not so bad. Again, if you see something funny happening, if you go back and try solving the other one first, that usually rectifies anything. If you get like a weirdo answer, it's like, holy smokes, I got too many angles in this triangle or something. That can usually be rectified there. Yes, sir?
For when you got R, how did you put that into your calculator?
What mode are you in? Are you in degree mode or radian mode?
Degrees.
Okay. So you just did cosine inverse of -11 over 80?
I did sine.
Oh, that would do it. So law of cosines has a cosine in it. Yep. No problem. Glad you checked. That's an obviously important piece to make sure, but okay. That's it for law of cosines, though, which is basically those two situations that you can run into, and we talked about the little things to worry about there. So that should be good. So last section is just about areas of triangles. So from geometry, what's the area formula for a triangle? Yeah. So if I give you some generic triangle here, what would the base be? It doesn't really matter, right? Any of the side lengths could be the base. But let's choose one to be the base for the sake of argument. Sound good? Which side makes the most sense to kind of think of as the base? Probably B, right? Since it's on the bottom of the triangle anyways. Just from a visual standpoint, that feels the most natural to me anyways. Okay, so what's the height then? Yeah, we have to draw an altitude here from angle B back down to the base, and that would be our height. That doesn't look very H-y. Let's do that. Okay. So how would I find that length for the height if I wasn't given it? Well, I could use the sine of angle A, should be equal to opposite over hypotenuse, or I could have done the sine of angle C equals opposite over hypotenuse, right? So H would be C times sine A, or it could be H equals A times sine C. So we picked B for our base here. So my area then is 1/2 B times C sine A, or it could be 1/2 B times A sine C. And if we had chosen a different base and we redid this problem, you could also get the other letter combination. So there's our 3 different versions for that area formula. 1/2 BC sine A, 1/2 AB sine C, and 1/2 AC sine B. So again, whatever 2 legs you're not using, or whatever leg you're not using, it's that angle is what goes in the sine. So let's say we want to find the area for this triangle. I'm going to just sketch a quick little picture to make sure that this is a triangle that's possible. And since we're in a side angle side situation, we're good. We can't run into an impossible triangle in that situation. So we can just plug this all into our formula and go on about our day. What would you do if you weren't given like the side angle side situation and asked to find the area? You might have to use the law of sines or law of cosines first to get the other piece that you'd need in order to finish using the area formula. That would be as hard as what problem like this could get, is where you have to stick in, like you have to solve for one extra piece before you can use the area formula. But it's not too bad still. Everybody okay with that? Okay. There's an additional area formula that we can use for a side-side-side situation. This is called Heron's formula. And it says for S equal A plus B plus C divided by 2, the area is the square root of S times S minus A times S minus B times S minus C, where we call S the semi-perimeter. So the perimeter of the triangle would just be A plus B plus C, right? The sum of the 3 side lengths. If you divide it by 2, prefix for dividing something in half is semi, right? If you have a semicircle, it's like half of a circle. Everybody's okay with that notion? We're going to actually derive this formula because it's an interesting exercise. Now, with any derivation, would I ever ask you to repeat this on a test or a quiz or anything? No. But because this is an honors course, this is the kind of thing that's like, you know, that we're interested in. So the way we're going to start Heron's formula is I'm going to use my previous area formula. Everybody's okay with that? So that's just the previous area formula. And we're going to multiply both sides by 4. Now, why we're multiplying both sides by 4 is probably not totally obvious, but eventually you'd come to that conclusion that you needed to do that. And it's easiest to do it now in terms of showing the walk through. So I'm just going to go ahead and do it now. And then I'm going to square both sides. Okay there. Next up, I'm going to replace sine squared using a identity. So I know from my Pythagorean identities that sine squared is the same as 1 minus cosine squared. And then I'm going to distribute through that 4a squared b squared. And now if I look at the right-hand side, this appears to be a difference of 2 squares. So I could think about it that way. Everybody's okay with that? So we can, yes, Ben? Oh, I just forgot the squared. Nope, thank you. I just got excited, you know. But before I apply the difference of 2 squares factoring pattern, I'm going to make another substitution here involving this piece. So if we recall, one version of the law of cosines is this, right? If I subtract a square, well, let's do this. Let's subtract the c squared over and then add this other piece over. So I'm going to add over the ab cosine c and then subtract over the c squared. Everybody's okay there? So now I'm going to replace 2ab cosine c with a squared plus b squared minus c squared. And then I'm going to do my factoring. Oops, forgot my 2. Okay. So my difference of 2 squares, I'm going to have 2ab minus a squared plus b squared minus c squared times 2ab plus a squared plus b squared minus c squared. So far, so good. I know it's getting ugly, but it's about to get a little bit neater here. So I'm going to go ahead and distribute the negative sign through. So that's going to give me negative a squared minus b squared plus c squared plus 2ab. I don't know why I wrote it in that order. And similarly over here, actually let's write it in this order. It doesn't really matter here, but I'm going to do this because it'll make it a little bit more obvious what I'm about to do. I'm going to do that. Or write them in that order. And the reason I'm going to do that is because these two pieces factor. Right? Those are both like perfect squares. So I can factor those. And what I'm left with here again is another difference of two squares in each of these factors, right? So c minus a plus b, c plus a plus b, a plus b minus c, and then a plus b plus c. Okay. So I'm going to go ahead and distribute through these subtraction symbols so I can get rid of that inner set of parentheses. Oh, boogers. I made a boo-boo. So it's here. That should be a subtraction symbol. So that should be subtraction. That should be subtraction. That should be subtraction. And then that should be addition. Sorry about that. I just got so excited. Ever happened to you? No. Disappointing. If you can't get excited about math, I don't know why. You know, what's wrong with you? I'm just joking. There's nothing wrong. All right. So I'm going to make a little claim here as like an aside. So c minus a plus b, I'm going to claim is equal to 2s minus 2a. So remember, s is a plus b plus c divided by 2. So the 2's cancel out. And then if I subtract the 2a, I have a negative a left, and exactly what I'm supposed to have, right? We see that? So I'm going to make that substitution. And I'm going to make similar substitutions in the other pieces. All right, let's see. That was 2s minus 2a. And the next one is 2s minus 2b. And the next one is 2s minus 2c. And the last one is 2s. Now, in each one of these sets of parentheses, I can take a greatest common factor of 2 out. So if I divide both sides by 16, 16 is 2 to the 4, so it'll cancel out all of those 2's. And then we just square root both sides. And because we're talking about an area, we can just drop the plus or minus. We know that areas always are positive. Well, let's say non-negative numbers at least, so we don't have to worry about that. So there's our Heron's formula derivation. Never would ask you to do that again. But just to kind of point out to you guys, a moment ago, I had said, well, what would you do to use the first area formula we talked about if you didn't have all the information? So let's say you're in a side situation. What would you have to do to use that other area formula? You would have had to use the law of cosines to find an angle, and then you'd have to use that other area formula, right? What two things did we really use to prove this? Well, we started with that other area formula, and at some point we had to substitute in the law of cosines. So it's exactly the same process, we just did it once really generally, and had to do some clever rearrangings, but it is exactly the process that we described. We've just streamlined it and done it once in a general setting to create a new formula that we can use kind of all the time. Okay. Let's just do one example using Heron's formula, and then we'll be done for today. Sound good to you guys? So let's say we have the triangle with side lengths 5, 8, and 10. Again, this is a side situation, so before we proceed, got to make sure that the sum of the legs is greater than the hypotenuse, or else you'd say no triangle possible. So our S in this case is going to be 8 plus 5 plus 10 divided by 2. That's like 11.5. And then to plug into our area formula then, I have 11.5 times 11.5 minus 5 times 11.5 minus 8 times 11.5 minus 10, all of which is square rooted, to give me about 19.810 units squared. So pretty easy formula to use. The derivation was kind of a lot, but the formula itself is pretty easy to use, and it's wonderful because you can do it kind of all in one line on your calculator, which is pretty rad, right? Not have to do a bunch of steps to do that. What do you guys think? So that's going to wrap up chapter 7 for us. So right now, our homework check is 1 through 14. Oh, we have that syllabus too. I guess I should put there. I'm going to also ask you to do worksheet 1 for that homework check. And then the rest of the problems and the review, I'm going to ask you to do for the next homework check. It doesn't seem very reasonable to ask you to do all of that over the weekend. You guys agree with that? Yeah, you guys have lives too. So let's see. So Tuesday next week is, what day is that? The 12th, right? That's going to be just the day we'll spend working in class on stuff and do a little bit of test prep on that day. So I'll tell you what the test is going to look like and all that jazz. And then Thursday next week, I think that'll be the 14th, we'll do the test on that day. Sound okay to you guys? Kristen? On 13? Sure. Yes, sir. Okay. Okay. So, Kristen, this one says 2 triangles can be formed. So we know this is the ambiguous case situation where we get 2 triangles. I'm going to go through anyways and pretend that it didn't have those instructions just to review how we can tell that. Okay. So if we have our triangle here, so 68, 19, and 18, this is an SSA situation, right? Because we have the angle not in between the 2 side lengths. And we have that our angle is acute. And we have the side opposite that acute angle shorter than the other one. So this is the ambiguous case. To tell whether we have 1, 2, or 0 triangles, we're going to do sine of C over C equals sine of A over side A. So I'm just going to set up a law of sines with the information that I have. And then sine A, when we cross multiply and divide, gives me 19 sine 68 divided by 18. And that number is 0.79, or 0.979, excuse me. Since that's less than 1, that's my indicator that I'm getting 2 triangles. Okay with that? So that's how I can tell that there's 2 triangles. Now the problem told me there's 2 triangles already, so I didn't really need to do that. But I think it's a nice thing to review because that's often the trickiest part of these, is figuring out the 1, 2, or 3 triangles. So the way I like to set things up is I make like a little list of what I need to find for each triangle and what I know about each triangle. And I use little subscripts for 1 and 2 to differentiate the parts of each triangle. That helps me kind of keep things straight, because it's sometimes just the information management is the hardest part of doing this, right? You have a bunch of information rattling around. It's sometimes tough to keep track of everything. So I'll start by finding angle A. In the first triangle. So I know that sine of A1 is about 0.979. So I'll just take the sine inverse of both sides. That comes out to be about 0.78152. And A2 is always just going to be the supplement of A1. So again, I like to do this by jumping back and forth between the two triangles. You could work straight down and do one triangle completely and then do the next triangle. That's fine also. That's the way I like to do it, is just jumping back and forth between them. So far so good, Kristen?
Yeah.
Okay. Now we can find the angle, the B's, really easily because we know two of the three angles in both situations. So that's 33.848. And then similarly over here. I get 10.152. And now that I know angle C, or now that I have the other two angles, I can find side C. So I'm going to use, it doesn't really matter here. So let's do sine of angle A over side A equals sine of angle C over side C. So C1 is going to be 19 sine 68 divided by sine 78.152. And that comes out to be, oh, great googly moogly. What did I do here? I wrote down the information in the wrong spot here. This was supposed to be here. Did that make a difference somewhere else? No, that was just a copy error. Okay. Sorry about that, Kristen. Okay. So this setup down here is just wrong, but the other answers that we found were fine. Jeepers creepers, Mr. Kulik. So we'll do sine C over C equals sine. Now here, we're looking for side B, so I need angle B, which was 33.848. So B2 is 18 sine 33.848 over sine 68. That looks more better. So that should be about 10.813. And then in triangle 2, we're going to set this up the same way, but I have to use the angle B from this triangle, which was 10.152. I don't know why I wrote B2 there. This is B1. So 18 sine 10.152 over sine 68. which is about 3.422. Does that feel a bit better, Kristen? Yeah, and again, like I jumped back and forth between triangle 1 and triangle 2. If you want to work all the way down and do all of one triangle first and then all the other triangles second, that's fine as well. Like it doesn't really matter. It just, since I'm doing basically the exact same work, to me, it just jumping back and forth is easy, but it doesn't really matter. Whatever makes more sense to you in terms of managing that. You're welcome. Okay.